Hello and welcome. We're going to be going over the Physics 1020 Unit 3 practice problems from A-Star in Florida. So props to you. Thank you, A-Star. Okay, we're going to show how this calculator program for the TI84 calculator can do a lot of physics stuff, this and more. So first thing we're going to do is talk about question 1. Bicycle wheel rotates with constant angular acceleration of 1.2112 revolutions per second squared. If it starts from rest, what is the wheel's angular velocity and how many revolutions does it turn through after 4.0834 seconds? So look, this is going to be under the kinematics menu. And I know you're thinking this is just for straight line kinematics. Rotational kinematics will work as long as you're cool with understanding revolutions would be like revolutions per second squared. Same thing as like say meters per second squared. If you're cool with the units, you're good. And I do have a help menu explaining all that. So I have a help menu for every little subsection so you can kind of figure out what's going on if you're not sure what the letters mean and all that stuff. Because I know it's in English and you're like, how come distance is S? And you're like, well, it's probably from some German thing for displacement. I don't know. That's just how it is. So I'm trying to help out, guys. So let's go on. The first thing is going to be this V equals VO plus AT. We want to find, and this is what's cool, you can find for any of the variables, we're going to find the final velocity. Okay, VO stands for velocity initial, or velocity at time 0. That's going to be 0, because that's when it says it starts from rest. You know, in real life, that's cool to take a rest on the weekend or your day off. But in physics, man, that means velocity 0. Okay, the acceleration, I know you're thinking angular acceleration, but we can kind of still use the same thing. So it's 1.2112. Let me make sure I got that right. And then the time is 4.0834. And I'm assuming it's in seconds. So this velocity is going to be the 4.9458. Okay, so for that one, 4.9458. And then how many revolutions does it turn through? Now, again, we're going to use the kinematics. In this case, we're going to do the distance. That's what S is. It's distance traveled. So we want to find the final position. I should have called it SF, but we're just going to call it S. So what is the initial position? We're going to say that's 0. And then velocity at 0, like the initial velocity, is also 0, because remember, it's at rest. The acceleration is at 1.2112, and then the time again is 4.0834. Make sure I get that right. And then so it looks like it's 10.097868. I don't know. Let's see. We're going to go to 3 decimal places. So this is going to round off to 10.098. I didn't put the units because it already has the revolutions here, and that's revolutions per second. So we're good. 1 problem down, 3 left. We're just going to do the first 4 problems on this worksheet. Now, okay, so, wow, what distance from the fulcrum? So I think this is going to be dynamics. It's a balance beam question. So let me just go to the right thing first. It's dynamics here, and then it has a help menu, but I actually, because this is so complicated to me, I put help menu under the balance beam. So I'm going to go 4. And then it talks about rotation equilibrium when the sum of all torques. Torque is like a force times a, it's kind of like, think of like turning a screwdriver or something, or a wrench. Torque is force times distance from the pivot point. So if you have a cheater bar, if you're used to mechanics, that helps you increase the torque. And then it goes for simple balance. We can solve for distance or for force. It's kind of cool. Clockwise and counterclockwise. So I don't think that's going to be that important for this one. In this case, let's see, we've got force 1, distance 1, that 10.395 from the fulcrum should, okay, this is going to be F2. And then what is the distance? Now, if this distance 1 is in cm, the final distance would be in cm. Otherwise, you have to convert everything to meters. So just be careful about that. So we're going to try to find the distance. And then F1 is going to be that 30.641. And assume it's in newtons. And then distance 1 is that 10.395. And that F2 is at 27.597. There we go. And then that looks like it's going to be 11.54. I want 3 places out the decimal. So that one's going to become a 2 because it's the trailing number is 5. So 11.542 there. Okay, good. Halfway finished the first 4 questions of the worksheet. Good. Now, this one's a little trickier. Let me just read it out first. Sorry if I didn't read out number 2. But number 3, a torque of 50.244 nanometers in the counterclockwise direction is applied to a wheel on a fixed axle. A frictional torque of 10.372 nanometers also acts on the wheel. Okay, so friction is in the opposite direction of the initial force. So the net torque is going to be that 50.244 minus that 10.372. That's why it's important to calculate the net torque. The angular acceleration is at 2.0957 radians per second squared. What's the moment of inertia? So actually, we have to exit this for just a second. So we're going to have to calculate that net torque, the 50.244 minus 10.372. And then I get 39. So the net torque is 39.872. Okay, so we've got that. We've got the angular acceleration. We're going to find the moment of inertia. So got to go to programs. And look, if you do have a Python calculator, this thing can handle it, because I've had multiple people ask that on my mcstutoring.com site. You can go to TI basic programs. And this is, I think, PhysSolve 4B. I'm going to enter to run it. So we want to talk about, I believe it's rotational. I hope it is. Oops. Oh, rotational motion help. Oh, there we go. Has some things for us. That T-looking thing, I think it's torque. I don't know what it is. But torque, that alpha is angular acceleration, radians per second squared. Moment of inertia is I. And then L is angular momentum. Just so if you're not familiar with what all the letters mean. So we're going to go, looks like a TIA. Well, let's solve for the I. So looking for the TIA. Oh my gosh, it's giving us all kinds of stuff. Okay, we want to look like TIA, so that's the first one. And then what is a moment of inertia? I think that's the I. I hope it is. I hope it's the I. I'd be embarrassed if it isn't. Okay, the torque, what's that torque force? That net force, that's what you have to calculate for whenever you have that sneaky friction going on. So 39.872. And the alpha, that's an alpha. It looks kind of like an A, but it's a Greek alpha. 2.0957. There we go. And check it out. Our answer is going to be 19.02. And I'm going to round it up to 6 because the number after that 5 is 5 or higher, so that rounds that one up to a 6. So I got 19.026. Great, great. Oh my gosh, that was the penultimate question. Now the ultimate one. Okay. Now, oops, I have to quit. Actually, I don't have to quit this one. I can rerun it. Our uniform ring with a mass of 4.0087 kilograms and a radius of 20.068 centimeters is rotating at an angular velocity of 21.544 radians per second. What's the angular momentum of this ring? So, one thing to know, we have to do some conversion. So I'm going to go to the More menu, and I do have this on almost all of my science programs now, the unit conversion, because so many people have asked for it. I'm also going to have a density here pretty soon. So probably by the end of March, I'll have a density one and put that on all physics and chemistry solvers. So we're going to convert SI prefixes, right? So what are we starting from? We're starting from centi, which is 6 from the centi, right? And then what do we want to do? We want to go to, I think we have to convert to meters, which is just the unit. If there's nothing in front of it like kilometers, hectometers, megameters, it's just the unit one. So that's going to be option 4. Okay, and what is the value? It's 20.068. There we go. So converted value. So it's 0.20068 meters. So I do have that conversion there, which is pretty handy. Okay, we went to the More for the angular momentum, option 3. And then what kind of thing is it? Now, if you need help, again, always go to the help menu. You're like, okay, it's just depending, what everything is, and it gives you the formulas. So if you need the formulas to show your work, you got it right here. And then we're going to solve for ring here, option 2. And then it shows you, cool, it shows you this. So you could say, hey, L equals mr squared W. I think the W is the Roman letter for that Greek omega. It looks kind of like a W, but I have to use W here because TI84, like that's what it uses. What's the mass? I think it's 4.0087. And then what's the radius in meters? Okay, and I put it in meters, so that helps you out. And if you don't know, you can go to the help menu, and I think it tells you what units to use. 0.2. If it doesn't, put in the comments, dude. I read the comments, and it's like, hey, make sure you put this on all your things and tell me, and I do respond to that. That's why I'm doing this. A-Star sent me this PDF, and I'm like, hey, cool, let's rock with it or roll with it. What is the radians per second? So that's the angular velocity, the 21.544. And there we go. We get 3.478. And again, what's trailing that 0 is a 6. So I'm going to raise that 1, round up. 3.4781 kilogram meters squared per second. So here we go. Next video pertaining to this will be the rest of these questions, which I think are more hydraulics. Yeah, hydraulic stuff, fluid stuff. And then we've got 9 through 12, unfortunately, I have to use a chemistry program that I have. And then 13's kind of a unit conversion thing. So look, good luck. I will see you next time. Like if you like it, dislike if you dislike it. Subscribe if you want information. And again, this is available at mcstudio.com, which I'm sure will be in the link in the description. Okay, take care, and I'll see you guys next time.